The blast furnace is a colossal, fiery heart of industry, producing over 60% of world's hot metal. But what really goes on inside this reactor where temperatures soar to 2300 degrees Celsius? Today we will dive into hidden signal and secret language that operator use to control this inferno, ensuring both peak performance and safety. Imagine your furnace is secretly cooling down, yet the hot metal flowing out still seems normal. The earliest, most critical signal often comes from something called direct reduction. This is where iron oxide, instead of being reduced by gases, react directly with solid coke at extremely high temperature, a process that devours heat. If the rate of direct reduction increases, coke is consumed faster and the solid burden descend more quickly. What we saying running furnace, creating a domino effect that will ultimately chill the furnace. The tricky part, then what is the tricky part? This happens or before you see a drop in hot metal temperature or silicon level at the taphole. Modern operators are trained to spot this silent threat early, often through real-time monitoring of gas composition and burden descent, allowing them to proactively inject more fuel and avert a costly crisis. For a blast furnace to operate efficiently, hot gas must ascend uniformly through alternating layer of coke and iron ore. But here is the paradox. The permeability of this layer is constantly under threat. Too many fines, either from raw material or generated during reduction, can cluster and form dense, impermeable zone. This forces the hot gas to channel, taking shortcuts often along the furnace walls, bypassing the very ore it needs to reduce. The consequences are severe: wasted energy, poor reduction, and potential damage to furnace lining. The trick is precise control over raw material sizing and a careful burden distribution. Sometimes even strategically adding a specific a smaller coke particle known as nut coke can create a vital pathway for gas flow, maintaining stability and efficiency within the crucial sticky cohesive zone. Now, are coming to the next slide. Once iron and slag are molten, they drip down through the coke and collect in the furnace hearth. But tapping these liquid is a complex, delicate ballet. The sheer volume and level of this liquid in the hearth have a profound hidden power over the entire furnace. A high heat liquid creates immense upward pressure, pushing against the coke, the burden, and the critical cohesive zone. This can disrupt gas flow, slow the descent of new material, and even cause furnace damage. The gap time, the period between opening tap hole is meticulously maintained or managed to control this liquid level. And then there is the taphole clay itself, a highly engineered material, not just a simple plug. Its quite composition, designed for wear resistance and rapid curing, is critical for consistent tapping and preventing dangerous incidents like molten metal breaking through or an explosion caused by uh, coal backing up into the basal pipe. It's a constant battle to master this liquid. Now coming to this slide, from the outside a blast furnace looks like a static imposing structure, but inside it's dynamic, often asymmetrical orchestra of chemical reaction and physical flows. Gas flow, temperature, and even material composition can vary dramatically across its radius and around its circumference. Modern operators are not just watching gang, they are interpreting a constant real-time stream of data from thousands of sensors, cameras peering into the twir, radar mapping the body surface, and complex models predicting hearth wear. These sophisticated expert systems diagnose condition, anticipate problems like chilling or channeling, are seen advance and even recommend precise intervention. It's a testament to modern engineering where deep scientific understanding, advanced technology, and human experience converge to conduct a high performance industrial symphony, transforming the precisely controlled process. The blast furnace remains at the core of the steel production, but its operation is anything but simple. By understanding its hidden signal from the depictive rise of direct reduction to the critical balance of permeability to the delicate dance of casting liquid, we move beyond mere observation to true mastery of the inferno. This blend of science, technology, and human sight continues to drive the future of efficient, safe, and sustainable iron making.